So, we're going to start talking trigonometry. So we're going to do a little intro to trig. Do we have a test next week? Was that wishful answer or well-educated? A little bit of both. How can that be? Let's see. If we go to our canvas, we do. When? Wednesday? Why is it not good? Not much. I don't think so. But so we have exam 1 Wednesday, February 4th. It'll mostly be algebra review and whatever we do today and tomorrow. So just intro to trig. So when we start talking trigonometry, we talk angles first. So, we use degrees to measure angles, right? We can use degrees. And basically it looks something like that. So we have some angle here. We will usually use Greek letters to denote our angles. Let's call it theta, a Greek theta. This side of the angle called the terminal side. And again, so if you measure your angles in degrees, you can have what is called a right angle, 90 degrees. Half of that would be a 45-degree angle. And so forth, right? Now, if you look at the full circle, if you start here, and then you rotate all the way around, right? What is the measure of that? So that's 360 degrees, right? Now, the degree measure is very arbitrary. It's very much made up. It's kind of fake measure. There is no reason why they decided. I mean, there is a reason, but there is no good reason why they decided that there is a 360 degrees in a circle, or 90 degrees in a right angle, or a quarter of a circle. Do you know why they chose 360? That's totally arbitrary. They literally got together and let's think about how many degrees. What? Well, how would that be connected? Yeah, so number of, what is it? Days, right? Could be. Number of days, very close, 360, 365, or whatever, right? That's one of the reasons. The other reason is that 360 is one of those numbers that's divisible by almost anything, except for some ugly ones, like 7, 11 does not divide 360, but almost anything else does, right? 2, 3, 4, 5, 6, not 7, 8, 9, 10, not 11, but 12, 13, yes. 14, no. 15, yes. So it has a lot of divisors. So it's very easy to, cut your pie in evil slices or whatever. But this measure, since really the degree measure, we don't consider that to be a real number. 90 degrees, I cannot put 90 degrees on the number line. Does that make sense? I mean, I can find 90 on the number line. It will not, the length from 0 to 90 does not represent the 90-degree measure. Because we eventually want to play with functions that take in the size of the angles and give us some outputs. So the degree measure does not really work for us as far as coming up with functions of real numbers, right? So we need to have some real number degree measure. Not degree, angle measure. And that measure is called radians. Radians. Radian or radians. Okay? The way we define the radian, here's an angle so let's say this theta equals 1 radian. The 1 radian is when the, if you think of this as a part of the circle, then this will be the point where the radius of that circle equals the length, the arc length over here. So let's call it S. So when R equals S, then theta equals 1 radian. Okay? So this way we can actually, yeah, so if the radius equals the arc length, so you open it to the point where this length right here equals this length right there. So when that happens, boom, the size of that angle is defined to be 1 radian. So then we can actually take whatever this length is and we can, put it on the number line. So 1 radian is now a real number. We connected the measure of an angle to a distance, right, to a physical length, which now we can place it on a real number line so we can locate that. Is that okay? So we can play a little bit with the radian measure, see whether we can take an angle. Yeah. If we can take, let's say, a 90-degree angle. And see what I can convert just without knowing any formulas. I mean, there are quick formulas that will tell you how to convert from radian measure to degree measure or vice versa. Or we can kind of come up with that on our own by just using the definition. Because if you think about this, the 90-degree angle, if I put it in terms of a circle, close enough? Just the letter. We use those types of letters to label angles. So that's the name of that angle. Okay. So if I look at a 90-degree angle, what do you think the length of this sector, the length of this arc, with respect to the length of the entire circle? I mean, what ratio is this arc to the entire circle? What do you think? 1/4, right? So the arc length here, arc length would be, yeah, so it's the circumference, right? Circumference of the circle over 4. Right? Now, just to make it easier, I mean, we can make it more general. Let's make this radius equal 1 for now. Let's just hypothetically say the radius of the circle is 1. And we'll be liking our circles to have radius 1 for a while. Well, what is the circumference of this circle? How do you find the circumference of the circle? It's not just 4. No, that's the area. Yeah, pi times diameter, or 2 pi r, right? The circumference of a circle is 2 pi r, right? That's the formula. Now, if r equals 1, in this case, if r equals 1, the circumference is 2 pi, right? So if I plug that in, I'll get 2 pi over 4, so that's pi over 2. So this is the radian measure of a 90-degree angle. I mean, I can actually plug it into the calculator. So the 90-degree angle is whatever the pi is. Here's pi. So here's pi over 2. So a 90 degree is a 1.57 radians. Now, we ever use this number, 1.57. We just think of it as just pi over 2. That's going to be easier for us to think of this angles in terms of pi. So 90-degree angle became, so 90 degrees is equivalent to pi over 2 radians. Does that make sense how we came up with that? We can do the same thing with a, let's say, 60-degree angle. So if I look at the 60-degree angle, and I think of this in terms of a circle, if the angle is 60 degrees and I make a circle around it, then the ratio of this arc length to the circumference should be 1/6, right? Because 60 degrees goes into 360 6 times, right? So then the ratio here will have the circumference of the circle divided by 6. And again, if I let the radius be 1, then that becomes 2 pi over 6, or pi over 3. Right? So the angle measure, so the radian measure with 60-degree angle is pi over 3 radians. Again, whatever that means. Okay? We don't need to know what it equals numerically. We just think of this as pi over 3. Pi over 3 is a real number. I can plug it in the calculator. It's 1 point whatever. And it's not important. We're just going to think of this as pi over 3. (180-degree angle). This one we can do really fast. It's either double of a 90-degree angle, or it's a triple of a 60-degree angle, right? If I multiply the 90 by 2, pi over 2 times 2 is pi. If I multiply 60 by 3, pi over 3 times 3 is still pi. So 180 is equivalent to just pi radians. Right? You just double the 90 degree to get to 180. Okay? So basically we can actually notice the way we convert. There is a general formula just by observation right now. We can say that to convert from degrees to radians, I will have to use the following formula. I'll take the degrees and I'll multiply it by pi over 180 degrees. So whatever the degree measure multiplied by pi over 180, 180 in degrees will reduce to some point, and then you'll come up with the answer. Okay? So therefore, to convert 270 degrees into radians, we'll go to 70 degrees times pi over 180. So degrees cancel. 270 and 180 have a common factor of 90. 90 goes into 73 times, 90 goes into 180 twice, so this whole thing becomes 3 pi over 2. So 3 pi over 2 is the radian measure of 270 degrees. How's that? Pretty straightforward. So that's to convert from degrees to radians. We can go back. We can go from radians to degrees. Convert from radians to degrees. So we can algebraically solve for degrees here, right? If degrees times pi over 180 equals radians, then then degrees equal radians times 180 over pi. So we'll go radians equals 180 degrees over pi. I'm sorry, not equals, times. So to convert from degrees to radians, from radians to degrees, we'll multiply the radians by 180 over pi. Okay, cool. So for example, 1 radian is 1 times 180 over pi. So I can actually, if I plug that in, I'll know the exact measure of 1 radian in degrees. It's about 57.3 degrees. So this is when the length of the arc equals the radius. It has to open to almost 60 degrees, so 57 point. Whatever this number is, pretty ugly number, but that's what we get. How's that? So far, so good? Now, so 1 radian is 57 point, let me be more precise, 2958. 2958 degrees. Now, we usually don't like using a decimal form for degrees. There's an alternative way, right? Know what I'm talking about? In a circle, there are 360 degrees. But if I take just 1 degree, we split 1 degree into 60 minutes. Because again, the degree measure is very arbitrary. So we're just kind of doing this, as you pointing out, the year thing. Okay? I don't know. So there are 60 minutes in 1 degree. And guess how many, if I take 1 minute, and actually the way we use the symbol for the minute is kind of this little prime. So a little circle stands for degree, 1 little, whatever you call that, stands for minutes. Now, what? Well, that's what you would call it in English or whatever. We'll call it, I don't know, prime. Actually, that is called minute symbol, so that's minutes. Now, how do you think we dissect a minute? Minute has 60 what? Yeah, seconds. So that's 60 of those. So that's the second notation, kind of a double prime. Okay. So I can actually convert 57.2958 degrees into its 57 degrees. And then how many minutes? So it's whatever the ratio of 29 to 60. So that's almost, what? Yeah, it's almost a half. So that's how many? Yeah. minutes, and then whatever 58. No, 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 that's not how I want it. I don't want to divide it, right? Point, let's see, 0.29 degrees into minutes. You just multiply, right? So it's 0.29 times 60, so it's slightly less than. Oh, that's right. Yeah. So how many? 0.29 times 60. So yeah, so that's how many? Yeah. No, that just makes my life a little more joyful. So basically, this is the story. So it's about 17 minutes and whatever 58. If I convert that, 0.58 times 60, so it's 34, 35 seconds. Hmm? Yeah, it's pretty close. So 0.58 is slightly, it's bigger than a half. So, no, no, no. It's like 0.58 as out of 100, right? So it's slightly bigger than a half. I mean, if we just round it, that will make our life a lot easier. If I just say 57.3 degrees, if I just did that, if I rounded 0.2958, then you know 0.3 off. Well, the third would be 20 minutes, but 0.3 is 18 minutes, right? 0.3 of an hour, it's 18 minutes, right? It's not a third. Third would be 0.3333. That would be 20 minutes. So this was equivalent to saying 57 degrees in about 18 minutes. Just one little bar. Right? If I ask you meet me 0.3 of an hour from now, that would be 18 minutes from now, right? You agree with that? If I ask you meet me quarter of an hour from now, you would say 15. Good. I was running into some issues with students in the learning lab over the past few years who just thought that a quarter is always identically 25 because of the quarter. So a quarter of an hour would be 25 minutes. Quarter of a gallon would be 25, whatever parts of a gallon is. So yeah, that was dangerously. Okay, just making sure we are on the same page. Okay. Now, let's see if we can visualize a degree with this measure, 500 degrees, right? How would that happen? What would need to happen? So let's say you start here, and then I'm going to start opening my terminal side. Let me do it like this. So here's my terminal side, right? And I want it to be 500 degrees, right? So I'm kind of starting at 0 degrees, and I'm going like what, 30, 60, 90, 180, 270, 360, right? So how do I get to 500? I keep going. So 360 plus 90, where am I at? 450. So I need another like 50 degrees or so from that point. So this will be 500 degree angle. I would go like that. Yeah. But 500 degrees is equivalent to what? 140 degrees. Right? Because you just rotate 360, you're back where you started, and you go a little further. Right? So I can actually, again, I can convert in radians. I will look at 500 degrees times pi over 180, right? I can reduce it to what? I can reduce both by 20, so it's 25 pi over what? 9, right? Or 140 degrees, I can do the same type of math on 140 degrees. That reduces to what, 7? 7 pi over 9. So these two are equal. So this is equivalent to 7 pi over 9, right? Because the 2 pi, right, the 360 degrees would be equivalent to 2 pi in radians. So you're just really taking the multiples of 2 pi out of that. 2 pi is 18 over 9, right? 18 over 9 gives you 2, so you just subtract 18 from 25 to get 7. So later, when we'll be dealing with these larger angles, we'll have to kind of put them back into this reduced form, and it will be a lot more friendlier. Either 148 degrees or 7 pi over 9 radians. But basically, you're just taking out the multiples of either 360 degrees or multiples of 2 pi radians to get to that. No, it's actually, this is now irrelevant of radius. We don't even have a radius. It's just a random angle, not a part of the circle. So radius is no longer part of the equation. Now we can also have negative degrees, negative angles. So we agreed originally that the proper way to start an angle is to go counterclockwise. This is how we starting our angle measure. We start at 0, then you're opening counterclockwise, going 90, 180, and so forth. Is that right? Are you with me? This is the original rotation. Now, if I ask you to envision the angle, let's say negative 30 degrees, so what negative sign does, it tells me that instead of opening up my angle counterclockwise, we'll do clockwise. So if I go 30 degrees in the opposite direction, that will give me a negative degree angle. So this thing right here is negative 30 degrees. We went down. Is that okay? So this is basically how we define things. But there is another way that I can get to this point, right? Instead of going 30 degrees down, I can go in a regular rotation, how many degrees to get to that point? 330, right? So negative 30 degrees is equivalent to 330 degrees. So you either go 30 degrees down or 330 in the regular direction. So now I can express the same thing in radians. The negative 30 degrees is equivalent to negative pi over 6 degrees. Right? We just converted. Or you can say that in order to convert negative pi over 6 to a positive degree, you'll just add 2 pi to it. So it's negative pi over 6 plus 2 pi. It's the same as negative pi over 6 plus 12 pi over 6. So it gives me 11 pi over 6. Well, because again, you go the other way. So you're adding 2 pi, the full rotation. Just like here, well, how did you go from negative 30 to 330? You told me that. How'd you get that number? Same thing. Full rotation is 2 pi, and you subtract from full rotation. That's what you did. 360 was the full rotation. You subtracted 30 from 360. Yeah. Right? I mean, well, we talked here. 180 degrees is pi, so 360 degrees. How many pi's would that be? Yeah. So but just 180, half a circle. So the full rotation then is, in terms of radians, 2 pi. Are you with me? Why? Right. So the 6.28 or whatever, that will be the radian measure of a full rotation. But we don't think about it like that. We just think of this in terms of 2 pi. This is enough for us to think of this as a full rotation. Another quick way to check, just think of pi as 180. So if pi is 180, 180 over 6 is 30, 2 times 180 is 360, and so forth. So 11 pi over 6, if you let pi to equal 180, 180 divided by 6 is 30, 30 times 11 is 330, so you still get the same measures. Okay? All right. Good. So this is just a little games we'll play with angles. Now I want us to talk about similar triangles. So similar triangles are triangles of the same shape. So they have the same shape, different sizes. But if the shape remains the same, then all the ratios of all the sides remains the same. So for example, if I have a triangle that has a side, I don't know, 2, 5, 7, right? And then I have another triangle that has the same shape, only it's bigger, and let's say this side is 11, I can find the rest of the sides in this triangle. Because I can set up little ratios. I can, let's say, call this side A and this side B. So for example, if these two triangles are similar, then the ratios of any side in one triangle to the same location of a side, another triangle, is equal as the ratio of, let's say, another pair of sides. So in this case, I could say that 2 over A is the same as 5 over 11. So I'm setting the ratios of identical sides as far as the location goes. Now, these ratios have to be the same, or you can take any ratio inside one triangle, let's say any two sides, 2 to 5. 2 to 5 has to equal to the same ratio of similar sides on another triangle. So if I'm doing 2 and a 5, then another triangle, the sides are A and 11. So these are equivalent ratios, really. So you can take any pair of sides in one triangle, divide them, whatever that ratio is, it's going to equal to the ratio of the same sides in another triangle. Or you can take one side from one side from the other, one side from one side from the other. So that ratio will be the same. Basically, it will tell you by how much one triangle is bigger than the other. But anyways, setting up the ratios like that, I can solve for A, right? If I just look at this equation, how would you solve for A just algebraically? Right. So you guys give me solutions. I'm slower than that. I'm just going to cross multiply, right? So that's 5A equals 2 times 11 is 22. So A equals 22 over 5, whatever that is. Right? I'll do it the same way here. If I multiply by 11, I'll just get A by itself right away. So A would equal to 11 times 2, 22 over 5, right? So we still get the same answer, regardless how we set our triangles, right? In the first case, I took the ratio of sides from both triangles. First fraction, one side came from one triangle, the other side came from the other triangle. Second fraction, one side came from the first triangle, the other side came from the second triangle, right? You recognize that? Now in the second ratios, I actually kept each fraction came from same triangle, right? 2 and the 5 came from the first triangle, and 11 came from a second triangle, right? So it doesn't matter how you do that. So we're actually going to look at a very special group of triangles and then figure out what are those ratios inside, because it's irrelevant how big the triangle is, these ratios will be the same. The ratio of 2 to 5 will be the same as the ratio of these two sides, okay? So no matter how far you stretch those triangles, the ratios will remain the same. So first triangle that I want to study is a 45-degree triangle. So 45, 45. Okay. So all triangles that have these degree measures will produce the same ratios on the inside. So to make my life simpler, I'm just going to label this side as 1 and that side as 1, because it's an isosceles triangle, so these two sides have to be equal. So the only side that I need to find is this side right there. Is there an easy way to do that? How would we do that? Yeah, that's right, because it's a 90-degree angle, so it's a right triangle. So whatever the side is, let's call it C, for the lack of a better word. We know that 1 squared plus 1 squared equals C squared, right? The Pythagorean theorem. So therefore, C squared equals 2, and therefore C equals square root of 2. Is that okay? So then if I take, let's say, the ratios, let's call this side A and this side B. Let's say the ratio of A to B in this triangle is just 1 over 1 equals 1. Right? So that means if you take any 45, 45, 90-degree triangle, doesn't matter how big it is, and you take the ratio of the two sides that are opposite of 45 degrees, you're always going to get 1, regardless of how big that thing is. But at the same time, if I ask you what is the ratio of A to C, what would that be in this triangle? One over square root of 2, right? Is that a polite way to express that ratio? How would you make it polite? Yeah, I need to rationalize the denominators. We don't like seeing square roots in the denominator, so this is how you rationalize. 1 times root 2 is root 2, and in the denominator it's 2. So it's root square root of 2 over 2. Right? That's a more polite way of expressing that. If I ask you the ratio of, let's say, C to B, you would go ahead and say, well, it's a square root of 2 over 1, so just square root of 2. Okay, so this is our 45, 45, 90 triangle. So this was 45, 45, 90. The other triangle that I want to look at is 30, 60, 90 triangle. So again, all triangles that have the same angle measures will have same ratios. Okay. Now, the way I do that one is actually a little trickier. I will start with an equilateral triangle. Is that equilateral? Yeah, that's equilateral, right? Now, equilateral triangle has, it's a 60, 60, 60 triangle, right? And I'm going to bisect it. I'm going to drop a height from above. So I'm going to get a little triangle. I'm going to get something like that. Right, I have two smaller triangles. That's not right. I'll just draw one. That one is 45, 45 triangle. So I'm just going to take half of it. So here's a half of it. So this is 60, this is 30 now. Because in equilateral triangle, if you drop a height, it also bisects the angle. It also bisects the opposite side. Okay. So for the sake of making my math look easier, I'm going to say let this side equal 2. Because again, I can take any size of that triangle, doesn't matter. So if this side is 2, then how big is this side? Provided that height will also bisect the base. 1. So then I have a triangle. This side is 2, that side is 1. Can I find, let's say, this side? Let's go with B. What is B equal to? So we have B squared plus 1 squared equals 2 squared. So B squared equals 1, B squared plus 1 equals 4. So B squared equals 3. Right? So B equals square root of 3. So this side is square root of 3 in that triangle. So now having that, I can figure out some ratios. So again, let's call this is A. No, this is C. And this is A. So in this triangle, I can ask you, well, how about A over C? What is that ratio? And you will say 1/2, right? I can ask you, what is A over B ratio? Right? Because you go 1 over the square root of 3, but then you'll have to rationalize that. So you'll multiply this by square root of 3 over square root of 3, which is square root of 3 over 3. Right? How about B over C ratio? So B over C is square root of 3 over 2. And again, I can just set up anything in this case, right? And again, these ratios will be true regardless of the size of that triangle. Okay? Regardless. Let me give you an example. Let's say I have this triangle, well, not drawn to scale, but I will tell you that, this is 45, this is 90, right? And let's say this side is 8, given, all right? I'm going to ask you to find this side right here. Okay? I cannot use Pythagorean theorem, because in order for me to use the Pythagorean theorem, I need to know at least 2 sides, right? To find a third side. I don't know the Pythagorean theorem, but I know that in the 45, 45, 90 triangle, the ratio of one side to the bigger side is always going to be square root of 2 over 2. right? A over C is square root of 2 over 2. We already found that, regardless of the side. So I know that the ratio of x to 8 always going to be square root of 2 over 2 in that shape of a triangle. So I can find x now, right? So x equals multiplied by 8 for square roots of 2. Without using the Pythagorean theorem, I can now do that, provided it's one of those triangles that we just talked about. Similarly, if I give you a 30, 60, 90 triangle, right? And I'll tell you that this side is 5. Can you find the other two sides? Can you tell me what this side equals to and that side equals to? Using these ratios? Yeah, so this ratios will stay the same. You just have to compare. Like, for example, what happened? Anyways, so I guess it's here now. The ratio of A to C is always going to be 1/2, right? So the ratio of a smallest side to the largest side is always 1/2 here. Well, now I'm looking at this. Okay, I know the smallest side. Can I find the largest side? 5 to C always equals 1/2 for these triangles, right? So therefore, what C has to be? 10, right? So C equals 10. You can now use Pythagorean theorem to find A, because you got two sides, or you can say something like this. The middle side to C, so in this case, A to 10, will always equal root 3 over 2, right? My other triangle is labeled slightly differently, but it doesn't matter. The ratio of a middle side to the largest side is root 3 over 2. So, you solve for A. A equals what? 5 square roots of 3? Well, let's do the math. What do? You just multiply by 10, right? The other side. 2 goes into 10 5 times, so it's 5 square roots of 3. So that's that. So we can find these sides without even touching the Pythagorean theorem. We could have used the Pythagorean theorem when we have both sides. But even starting with just one length, you can find the rest of them, provided it's that shape, 36 to 90 or 45, 45, 90. We can only do those two triangles analytically. Now, Arthur is wondering, what about 37, 53 degrees, 90 degrees? And at least I'm keeping it 90. I can do that. I need more theory. Yeah, of course it's possible. Then Jose is curious about, what about 37, 58, and whatever's left, which is no longer 90. Can we even do it like that? Can we only work with the right triangles, or can we just do any triangle? And the answer is, well, we can do any triangle. Yeah, we're that powerful. But we're going to start small, just these two triangles. And again, we just played with Pythagorean theorem. What's going on with my thing here? Okay. So, but now, and again, this is just, it's kind of a intro to trig. It's not even official section 6.1. We're in chapter 6 now, but it's bits and pieces of section 6.1. But there is one very important tool that we'll use throughout this semester, and you'll use it in Calc 1 and you'll use it in Calc 2. Anytime you're faced with a trig, you'll use this animal called unit circle. Now, how many of you know what I'm talking about when I say unit circle? Yes, 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 no. Okay, 2 yeses and 2 nos. What? You said no. So I had 2 yeses and 2 nos. So let's say I have a circle, kind of centered at the origin. Radius of the circle is 1. Is that okay? I can do it like maybe that if you don't like my... Is that good enough? Yeah, I want it to be... Yeah, it's okay, right? So it's a circle of radius 1, circle of radius 1, centered at the origin. Okay? Now, what is the equation of a circle of radius 1 that's centered at the origin? Just see whether you remember that from algebra. Equation of a circle. That's you giving me circumferences, you giving me some measures. I want to have an algebraic equation of a circle in terms of x and y. Anyone? It's not too long. No. Those are the measures of a circle, circumference area. I want to know, like, x, y type of equation that draws a circle. Yeah, it has that kind of stuff in it. No, you're just guessing. Yeah, remember the h's and k's? The general equation of a circle, it's x minus h squared plus y minus k squared equals r squared. The circle centered at hk of radius r. Well, in our case, since x and h and k are both zeros, because we're centered at the origin, and the radius is 1, this is the equation of our circle. Okay? Well, I want us to label some points on this circle, because this is a circle in the xy plane. Now, this point right here is easy to label, right? Radius is 1. What do you think that point is? 1, 0. What do you think that point is? 0, 1. What is that point? Negative 1, 0. And that point? Right. Okay, good. Well, now I want to do something. I want to get more points on this circle. I want to kind of draw a little line that forms, let's say, a 30-degree angle here. Okay? And at some point, that line intersects the circle over there. Okay? I want us to find the coordinates of that. Oh yeah, we can do that. Because look, so this is 30-degree angle, right? But see what happens. If I also bring down a height here, this will form a 90-degree angle. So what would be that angle right here? If this is 30, that's 90, 60. Okay, that's a 60, right? So this is our 30, 60 kind of a deal, right? And what is the length of this side right here? 1, right? Because that's the radius of the circle. So that side equals 1. Right? So right away, since we already did this triangle, if you look, the ratio of the smallest side to the biggest side is 1/2. Right? So this side, therefore, is 1/2. Right? We already did that. Look at your notes. We did the ratio of the middle side to the largest side was square root of 3 over 2. Right? So this length is square root of 3 over 2. That length is 1/2. So then what is the x value then of that point? Provided that this length right here is square root of 3 over 2. What is the x value? Square root of 3 over 2. What is the y value? 1/2. So the literal location of that point is square root of 3 over 2 and 1/2, the coordinates. Now notice how if I take that x and y value and I plug it into the equation of my circle, it will make it work. If I take square root of 3 over 2 and I square that, that becomes 3 over 4. You agree with that? I'm not going to write it down, but if you take root 3 over 2 and you square that, it becomes 3 over 4. You take 1/2, you square that, it becomes 1/4. So 3/4 plus 1/4 equals 4/4, which is 1. So that point works. So okay, so we got that point down. Now let's do it again, only now I'm going to come up with a 45-degree invisible line. So I'll hit this point right here, and I want to find the x and y coordinates of that point. But in the same fashion, I'm looking now at a 45, 45, 90-degree triangle, right? I'm looking at this triangle now that we already played with, right? Now this side equals 1, right? This side, the one that's opposite of a 90 degrees is a radius, so it equals 1. And if you go back to the ratios that we have discovered, then these two sides will come out to be square root of 2 over 2 and a square root of 2 over 2. We already did that somewhere here. The ratios of the smaller side to the circumference is going to be, to the radius is square root of 2 over 2. So if c equals 1, a equals root 2 over 2, right? Because c equals 1 right now. And same thing, well, that's all I need, right? So just from whatever this we discovered before. So therefore, x and y values are the same here as the square root of 2 over 2, square root of 2 over 2. These are my points, just using it's the same triangle. Right? The x and y value will be equal in this case. That side equals that side, and that side is 1. And we already found all the ratios. So it's root 2 over 2 all the way around. And again, if you take that point and you plug it into my formula for the circle, square root of 2 over 2 squared becomes 2 over 4, which is 1/2. So you have 1/2 plus 1/2 equals 1. What? Well, because it's this triangle, right? It's that triangle. Only now c equals 1, because we drew it in a fashion that this side, the largest side, equals 1. So we have this formula, right? Here it is. A over c equals square root of 2 over 2. Well, c equals 1 right now. So that means a equals square root of 2 over 2. So that's it. A is one of those sides, so it's square root of 2 over 2. The other one is equal to the first one, so it's 2 roots 2 over 2. So I got that point now. I got the x and y coordinates, because this length now is root 2 over 2, so that's the x value. And this length is also root 2 over 2, so that's the y value. Okay? I'm going to do the same thing again. Now I'm going to draw a line under the 60-degree angle. So again, if I drop a height, I'll get my 36 to 90-degree triangle again. So I'll have the same points, only in reverse. The coordinates of this point right here will be 1/2 and square root of 3 over 2. Just the same points, only the opposite. Because I'm looking at the same triangle. Only from, x became y, y became x. Did that make sense? Okay. So these are the 3 important points we'll use throughout this semester. But then I can get the rest of the circle. I'm going to use symmetry. Because look, I have a point here. So if I just draw a line, I get a point here now. Can you tell me the coordinates of this point right here? If that point is 1/2 square root of 3 over 2, what is the coordinate of that point? Negative 1/2 and same root 3 over 2. Right. So it became negative 1/2 root 3 over 2. Same thing here. X became negative root 2 over 2, and then root 2 over 2, right? And then the same point here. That gave me a negative root 3 over 2 and 1/2. So the x became negative, y stayed the same, right? If I go here, now both negative, right? Negative root 3 over 2, negative 1/2. I go to this point, negative root 2 over 2, negative root 2 over 2. I go to this point, negative 1/2, negative root 3 over 2. So both x and y are negative there. And then I can do the same thing. Okay, this was supposed to be vertical. And I can do the same thing here, right? The x remains the same. Now y, only y is negative. I'll just keep going. So this is negative root 2 over 2, and just root 2 over 2, and then finally, you're right. Yeah. So x is positive, y is negative. Thank you. Just making sure you're paying close attention, because I clearly wasn't. And whatever that thing is, so I can move this point, let's say here. Oops. So what would that be? 1/2 negative square root of 3 over 2. So these are the, how many points is that? And then for more, so 16 points, right? You will need to know this unit circle. You will have a question on the first exam. Boom, fill it up. I'll give you a picture, you have to label each point. Now you notice how I did that, right? The only hard part, the only thing that you really need to memorize are these first 3 points. Do you agree with that? If you have first 3 points, then you just use the symmetry. You change the signs of x and y in an appropriate quadrants. Do you agree with that? So when I say 16 points, it really is 3 points, because the rest are easy. Do you agree with that? So that's not that hard of a question. Right? How many of you have seen the unit circle before? 2. You've seen it before, but you probably don't remember. Okay. Now that, well, anyways, so do you remember the unit circle? I mean, like, actually remember it? You haven't learned it new, you just knew that those are the points? Okay. Right. So now, so you see these 2 poor ladies had to memorize the unit circle, all 3 points, right? Again, that's the only thing you need to memorize. You do the symmetry from then on, right? But they made you memorize it, right? Yes. Now you want to get your money's worth? I'll teach you how to get the first 3 points for free as well, so you don't have to memorize it. No, I mean, I had to go through I just derived it the hard way, right? I showed you that this is the case beyond any doubt, not just reasonable doubt. We had to mathematically derive them. Now check this out. I will teach you how to create a unit circle without using any of your memory at all. You just have to use what? No. You just need to use your pattern recognition and maybe some imagination. Is that close enough? Nah. That's okay. So let me teach you. Who's going to have problems labeling that point? Nobody, right? Yeah, radius is 1, unit circle. Radius is 1. But you're right, if the radius was 5, then you can still label that point. But you all agree that, what is the coordinates of that point? 1, 0. Now, so I have 3 more points, right? Can you label that point? 0, 1. Okay. So far, so good. How much of a memorization have you used? None. Come on. That's no memorization. Now, raise your hand if you know how to count. Okay. So let's count. On integers, on the number line, I look at 0, right? What is the next integer from 0? 1. What's the next one? 2. What's the next one? 3. Now let's do the same here. You see 0? Let's count. Count. All right, well then put square root over each one of them and everything over 2. And we're done, right? That's it. The square root of 1 is 1. But yeah, because look, I got the same thing, right? Root 3 over 2, 1/2. Root 3 over 2, well, that's 1/2. Root 2 over 2, root 2 over 2. Root 2 over 2, root 2 over 2. Root 1, that's 1. So 1 over 2 and root 3 over 2. 1 over 2, root 3 over 2. Isn't that a lovely pattern? You go 0, 1, 2, 3, 0, 1, 2, 3. Take square roots of all and divide them by 2. And it will generate the first 3 points, and then the symmetry will generate the rest. Yeah, that is a coincidence. That's a pattern recognition type of situation. It's not in the book. Nobody will ever teach you that. Because this is a shortcut that's so awesome that you're like, nah, we'll just make them sweat and memorize. But then, this is lovely, right? So, but anyway, so this was, just unlock it. Let's see what I'm missing. So we got the unit circle. So, but again, this was of radius 1, right? But if the radius was not 1, but something else, let be for general radius r. So we have a unit circle x squared plus y squared equals r squared. Sorry, not a, what's going on? It is very relevant. Go sit your ass down. I'll let you go like in 5 more minutes. So this is a general circle centered at the origin still. Okay. Now remember, we agreed, every time I draw these little triangles, it's irrelevant to how big those triangles are. The ratios will stay the same. Okay. Are you ready for that? So anyways. No, you're not ready for that yet. Yeah, I'll let you go. Okay, good. We're done. You're not ready for this yet. Yeah, we'll continue this on Friday.